Swayam Prabha. Digital India. Educated India.
So in today's lecture in biochemical engineering, we're going to continue looking at immobilized enzymes, and we'll start from where we left in the last class, which was the mass transfer coefficient. So what we're looking at in the last class, if you remember, was our interphase mass transfer with reaction, right? So there was a flat plate. So if I'm to remind you, so we had a flat plate like this, and there's a boundary layer, say, and these enzymes are on receptors that are bound to the surface. And because this is a fluid phase, and this is a solid phase on which the enzymes are immobilized, so the enzymes are immobilized. So what happens is there is a transfer between the fluid and the solid phase, and that mass transfer coefficient was referred to as Kf. Now, what we didn't do or didn't get the time to do in the last class was how this Kf varies. How do we evaluate these Kf? It turns out that there are a lot of empirical relations to evaluate the Kf, the mass transfer coefficient. Now, what we looked at in the last class was flat plate. But what if it weren't a flat plate? What if it's a circular tube or a sphere or any other kind of thing? So what I want to show you on the screen today are these relations for mass transfer coefficients. These are for laminar flows for different kinds of geometry. So first one is flat plate, then circular tube, then solid spheres, and then finally falling films. So it's not So the first relationship is K observed times, that is K observed is observed mass transfer coefficient times Z over dm, Z being the distance. So this is the flat plate. So depending on where you are on the flat plate. So that goes as Reynolds to the power half and Schmidt number to the power 1/3. And then for a circular pipe, the Kf, which is the mass transfer coefficient, is given by Kf d over dm, d being the diameter of the pipe, over dm, the molecular diffusivity. That again goes as Reynolds to the half and Schmidt to the 1/3, but the coefficient is different. So the coefficient in the last one is like 0.3, and here it's 1.8, so it's like 6 times. So what you see is that one important similarity is that K observed Z over dm or K observed d over dm, whatever it is, Sherwood number actually, goes as Reynolds to the half and Schmidt to the 1/3. Okay, so how does it look when we have forced convection around solid spheres? This is something you probably have read in your mass transfer classes. Again, it goes as the same. It again goes as Reynolds to the half and Schmidt to the 1/3, but there is a little catch. The catch is that there is a constant. So because of the shape of the sphere, there is a constant with that. And if you go to the screen, this is what you'll see. The Sherwood number goes as 2 plus 0.6 Reynolds to the half and Schmidt to the 1/3. So that those two coefficients are there, Reynolds to the half and Schmidt to the 1/3, but you have the 2 plus. So, and finally, the last thing that we want to look at is the falling film. So the falling film, it turns out, is similar to the flat plate in the sense that its geometry is similar. Also, it's a flat kind of thing, and it goes again as Reynolds to the half and Schmidt to the 1/3, and the coefficient is 0.7, which is not too different from 0.3. So it's around twice that of the flat plate. So the difference that what would be the difference between a falling film and a flat plate? So this is if I go to this thing, this is a flat plate, right? What would be a falling film like? So this is again your solid surface, and this is how it is going to be, right? There is a falling film. So what is different over here is the effect of gravity. So this is a vertical, this is a horizontal. So the gravity is going to affect what? It's going to affect the size of the boundary layer and also the velocity profile in the boundary layer, right? The thickness of the boundary layer and the velocity profile in the boundary layer. So if you have take a falling film like this, okay, and compare it with a flat plate, so what is going to happen here is that that what you have at the bottom, this is going to, the liquid is going to drag in this direction, right? Liquid is going to drag in this direction. So as the liquid goes down, the z, or in other words, as the length goes down, then the size of the boundary layer grows, right? So as z goes higher, more and more you go down, the size of the boundary layer is going to grow because it's dragging, the fluid is dragging more in the vertical direction because of gravity. Is that okay? So so as a result of which, so the two things that are different over here are, A is the thickness of the boundary layer and the velocity profile in the boundary layer. Okay. And therefore the Sherwood number is slightly different from the flat plate. Okay. Is that clear? So what we are looking at till now are these cases. If you remember, all the examples we did in the last couple of lectures are examples where the enzyme is on the surface, right? The enzyme is on the surface, and either it's through diffusion or it's through convection that mass transfer is taking place. Now, what we're going to do now in today's, so that's the whole idea of today's lecture, is let's go to the screen, is intraphase mass transfer and reaction. So what is different in this one is that it's intraphase. So let me see if I have a picture here. I don't have a picture here. Let's see if I have a picture out here. Let me go back and show you some. So I can use this picture. So that's the difference, you know. So if, for example, if you have intraphase mass transfer, if the enzyme, immobilized enzyme that's there, is entrapped within the encapsulation, within the gel or the matrix, then there is no way for you to make it react with the substrate without the substrate actually diffusing into the enzyme, right? So that's the difference. So intraphase, intraphase is intra, within the phase. So mass transfer should happen within the phase. And when you have intraphase mass transfer, what happens is that the reaction occurs simultaneously, right? So that's a major difference. So this was an example where we had only the interphase mass transfer. So the solid was the enzymes are on the surface of the solid, and the fluid comes in and reacts. And in interphase mass transfer, the enzymes are on encapsulated within. Okay, is this difference clear? The physical difference. Now, in addition to this, you can have enzymes which are on the surface. In addition to it being entrapped inside, you can have enzymes on the surface. Okay. So now let's go and look at what the difference is and how to study this. What kind of models can we make? So the first important thing that I want to discuss over here is that the concept of pseudo-homogeneous reaction, and we did that before. So if I can, attract your attention to this. So my enzymes are, let's say these are my points of where the enzymes are. Okay. Now, if I can go and write a homogeneous model for this, okay, or a heterogeneous model for this. This is something I discussed, but I still want to go into the details and try and see if you can understand it completely. So if I am to do a heterogeneous modeling of this, what would I do? I would actually let the substrate diffuse to the surface, then from the surface diffuse in. Okay, why do I separate these two diffusions? The diffusion over here, so diffusion in fluid and then diffusion in this, because it's a porous solid here. So diffusion in the pores, the diffusion coefficient and all that stuff are going to be different. It could be Knudsen diffusion depending on if it's the pore size is very small. If it's not, it would still be different. The diffusion coefficient is still going to be different. So if I am to do a heterogeneous model of this, my step 1 is diffusion in fluid. Okay. Step 2 is diffusion in porous solid. Then step 3 would be adsorption, or you can just go straight to reaction if you want. Okay, reaction and adsorption, you can say. But what is the challenge that we face over there? The challenge that we would face over there is that we have to have a geographical map of where these particular enzymes are located within the matrix, right? If we are to allow, so because you are doing a simulation, if you're doing a simulation on the whole thing, you need, so the material, the substrate is diffusing into the whole thing, but for you to figure out that, for you to be able to quantify that, you need to know at which point it is reacting. What are these? Because see, what happens is within this matrix, these become almost like point sinks for the substrate. These points of reaction become point sinks for this substrate, and you need a map of where these point sinks are. So if you were to do a heterogeneous model, it's absolutely not impossible, but it's a little cumbersome in terms of the modeling. And then you have to do the diffusion out of the porous solid and out of the fluid. That's not the problem. The problem lies here. So what we do is we come up with what is known as a pseudo homogeneous model. What is the assumption of such a model? What is the assumption of a pseudo homogeneous model? What is the assumption of pseudo homogeneous model? The assumption is that you homogenize over the entire matrix. So you assume that these receptors are present uniformly in the entire matrix. So what you take is you figure out that what is the total number of receptors, what is the reaction rate for each, okay, and multiply that and get the total amount of reaction rate for the receptors, and then divide it by volume to get a volume average reaction rate. Is that clear? So that would be, so once that is there, then it is assumed that though these reactions are in principle heterogeneous reactions and they are occurring at certain points, you assume that the whole thing occurs uniformly over the entire matrix. Okay, so this is the concept of a pseudo homogeneous reaction. I am not sure, is that a new concept for you, or you've studied this before? No? New. Okay, so at least I hope it's clear, right? Because we don't want to get over this again and again. So let's go back to what we have on the screen. So this is a definition, it's exactly what I explained, but just to go through it. So heterogeneous reaction that occurs within a tissue or porous matrix contains immobilized enzymes are called interphase. Interphase, although the reaction occurs at the interface between the fluid and the cell surface or at the extracellular matrix, the phases within the tissues is considered to be pseudo-homogeneous if the reaction is macroscopically uniform. So this is a term that we introduce here, macroscopically uniform. What it means is that at the microscopic level, it's occurring at different points inside the matrix, but at the macroscopic level, it is uniform. And when at the macroscopic level it's uniform, then you can assume it to be pseudo-homogeneous. So it's a matter of scales, right? So it's a matter of scale. So if at the scale that you are looking at, okay, if at that scale your reaction is homogeneous, then you can assume it to be pseudo-homogeneous. But at the microscopic scale, it could be heterogeneous. Okay, this is the concept of scale. So at the smallest of scales, say for example, if you have a surface like this, okay, and you're trying to take the derivative at this point, which point do you take the derivative in? You never know. Or if you have a surface like this, okay, we can say that at the macroscopic scale, we can say that this is a singular point because you cannot define the derivative here, and this is a non-singular point, right? You can define the derivative here, but at the microscopic scale, this is not singular. You see what I'm saying? Because when you go to the level of at the microscopic level, this is no longer as sharp. This peak is no longer sharp because when you go to the microscopic level, so this is not singular. At the microscopic level, you can define the derivative at this point. Okay, so that's a matter of scale, the manner of looking. So the same thing happens here. So at the microscopic level, it's it's heterogeneous because these reactions happen at different points within the matrix, but at the macroscopic level you can average them out. They're macroscopically uniform, which means that you can average them out. And the whole concept of averaging theory, the basic concept of averaging theory originates from this, where you can actually decide that whether a system is macroscopically uniform or microscopically uniform, that kind of thing. So if it's microscopically uniform, fine, there's no question at all. But the whole concept of averaging comes in these certain issues or in these certain cases where the system is microscopically non-uniform, but at the macroscopic level you can decide. Now, how do you decide what is microscopic and macroscopic? That is a question that is important. And what typically is done is that let's call this R, okay, so is a microscopic length scale versus macroscopic length scale. If this is much smaller than 1, then you assume, so this is your criteria typically, you assume that it's macroscopically uniform. Okay, so the length scale at which you see this heterogeneity, so this is the heterogeneity length scale, and this is the non-heterogeneity length scale. So the length scale you see at which you see heterogeneity over the length scale at which you don't see heterogeneity, the ratio of these two have to be much smaller than 1, right? So if this is possible, then what you do is you can average it out over the macroscopic length scale, and as soon as you average it out, you get the pseudo-homogeneous model. So pseudo-homogeneous model is not a matter of just a matter of intuition. It is a matter. It evolves out of your averaging theory. So whether you, in the macroscopic, once you have done the pseudo-homogeneous, got the pseudo-homogeneous model, in the pseudo-homogeneous model, what happens is the assumption is that reaction and diffusion occur simultaneously. Okay, is that clear? In the real model, in real life, diffusion and reaction are not occurring simultaneously. In the heterogeneous model, diffusion and reaction are not occurring simultaneously. Remember, so first diffusion followed by reaction. But in the homogeneous model, pseudo-homogeneous model, diffusion and reaction are assumed to occur parallelly. So if this is just a corollary, so to say, if the reaction is too fast as compared to diffusion, the concentration at some places becomes 0 because now it's diffusion control. So this is one of the interesting things that can happen in a pseudo-homogeneous model. I mean, what a pseudo-homogeneous model cannot capture. So if you have a system like this, and say for example you have a reaction like an autocatalytic reaction that we discussed in the last class. So what can happen is, because the reaction at some places can, because if there is a small perturbation in the system, the reaction in some places could be much higher than the reaction in other places, right? So the concentration in some places, say for example, the concentration of the if substrate A here could be 0, and right next to, not too far from that place, the concentration could be high. So what will happen in that case? What will be the consequence of that? There'll be a major difference, a large difference in concentrations. It could be next to each other depending on the kinetics, right? If you have a kinetics of this type, A plus 2B giving 3B, then A could be depleted in one place and A could be far from depletion from another. It could be present in large amounts. So what will happen in that case? That's as a real system. I'm talking of the heterogeneous system now. No runaway. I'm just talking about catalyst pellet here. There cannot be a runaway in a catalyst pellet. So this is just a catalyst pellet, right? Catalyst pellet or a immobilized enzyme, whatever you want to call it. So what can happen? Well, what will happen is that the heterogeneous model is still fine, but you cannot average it anymore. See, there's no point in having an average when one part of that has a very large concentration and another part has a very small concentration, because the average value would not give you a sense, the right sense of the distribution. So when you want to average, the criteria number 1 is that the ratio of the smallest to the largest length scale is much lesser than 1. The criteria number 2 would be that the minimum over maximum concentration, minimum C over maximum C, should be of the order 1. Okay, there shouldn't be a huge difference. Okay, it could be 0.1, that's still order 1, but it could be, it cannot be, there cannot be a 10 to the minus 3 or 10 to the minus 4 within the matrix. Okay, so which means that the variation within the matrix has to be reasonable. There cannot be a very large variation. Okay, so having said these things, I think now that it doesn't make sense to go and write a model unless we understand what are the constraints, what are the boundaries within which we are writing that model. So having met that, so let's we can try and write a model for this. So what we do is, these are for drugs, biomolecules, therapeutic molecules, and so on. And if the diffusion is slow, then reaction rate could decrease significantly. The reason is because this is diffusion and reaction occur parallelly, but in real life diffusion precedes reaction. So if diffusion is very slow, then reaction obviously would be hampered. It's straightforward. So what we do is that in the pseudo-homogeneous model, what we write over here is d effective Laplacian of C minus R of V, right? Do you all remember, by the way, how to write your Laplacians in spherical and cylindrical and all these coordinates, because they'll be in the test. So why d effective? Why d effective? Because this is not the real diffusion. Excuse me. So this is not the real diffusion, right? The real diffusion occurs in the spaces between the pores. So this is the effective diffusion coefficient, because we have taken an average out of the whole thing. So the diffusion coefficient is also an average between the diffusion coefficient of the solids through the solids and the spaces between the solids, right? Okay. So R of V is, let's define RV average as the macroscopic reaction rate. So what would be the macroscopic reaction rate? As I said before, the summation of all the microscopic reaction rates over the volume, right? Divided by the volume. So R of V average is the summation of all the microscopic reaction rates divided by the volume. Fine. So this is given by 1 over minus 1 over V. So why is that? So this is, you can replace what you have over here, the diffusion reaction problem, from here to here. Okay, and then what you do is you simply use the Stokes theorem. Clear? So just change the Laplacian to the surface integral. Very straightforward. I think you've done this before, changing from the Laplacian to the surface integral. So when you do that, then this is all fine. So you can write your R average in these ways. So the advantage with this writing is that you just need to, changing from the volume to the surface, is that you just need to evaluate what's going on in the surface. You really don't need to care about what's going on in the volume, right? So then we define this quantity eta. Eta is my effectiveness factor. Okay? And I think we did effectiveness factor in the one of the lectures before also, right? Couple of lectures back. No? Okay. So this is something that we're going to do for the next couple of lectures. So let's try and see what the effectiveness factor is. So the effectiveness factor is essentially the reaction rate when the reaction is occurring over the entire region, over the reaction rate if it were only occurring at the surface concentration or only occurring at the surface. Okay. So if the entire, or in other words, if I am to explain a little better, if the entire concentration, if the entire amount of material were at the surface concentration, so that is my denominator. Okay, entire material in CS, surface concentration, over the actual reaction rate that happens. Okay, and this actual reaction rate we can obtain, as I showed here on the screen. You see actual reaction rate you can obtain as the volume average. Fine. So why is this important? Because see, for a material, once you have evaluated what is your effective reaction rate, if you want to know your actual reaction rate, all you need to do is evaluate the reaction rate at the surface. Okay, and effectiveness factor, and this is essentially the effectiveness factor, and this is a very important thing that some of you are taking the advanced reaction engineering course. Are you? Any of you? Not taken. So then you will study these things, you know, the effectiveness factor. So the effectiveness factor essentially measures that if a reaction is occurring at a certain, if a reaction were occurring at the surface concentration and if the actual rate of the reaction, the ratio between these two. Okay, and we'll see how to incorporate that in the next few cases. So this is okay. It's not important. So what we do now is that now let's go and actually do a problem, solve a problem. So the first problem we look at is interphase mass transfer and reaction in a rectangular slab. We'll look at in the sphere and the rectangle. So first thing we look at today is this problem in the rectangular slab. Okay. So what is my basic governing equation for the rectangular slab? What is my governing equation for the rectangular slab? In this case, interphase mass transfer and reaction. It's, you know, right there in the title. If you look at here, interphase mass transfer and reaction in the rectangular slab. So these are entrapped. These receptors are entrapped inside. So what would be my governing equation? So what's the basic phenomena? Let's talk about it first. So essentially, the basic phenomena is a heterogeneous reaction, but we are going to use a pseudo-homogeneous model. So let's make that clear first, that we are essentially it's a heterogeneous phenomena, heterogeneous system, but we are going to use a pseudo-homogeneous model. What is the basic assumption of a pseudo-homogeneous model? That reaction is uniform everywhere, and you can use an average reaction rate A. B is that because you use average reaction rate, diffusion and reaction occur parallelly. So what would be my model now? Yeah. So my minus B effective Laplacian of C should be equal to minus R of B. Okay. So this is my diffusion. Reaction, because this is being, you know, C is a substrate, so C is a substrate concentration. So this is a reaction as a sink term because it's being consumed. Fine. So the reaction rate. So this is my basic equation. The reaction rate is here given as Kv times C. Okay. So the Laplacian the effective times Laplacian of C equals Kv times C. Okay. Now what would be my boundary conditions? Let's talk about that. There are several possibilities with boundary conditions, but let's talk about boundary conditions. So what are my two boundaries? One would be at the center, right? Because we are going to, this is a symmetric width. We have to assume, so it depends on what we assume. If we assume Laplacian to be a symmetric Laplacian means in this case what would we have? Okay, let's I think you don't really remember all the Laplacian things. So this is a this is a rectangular slab, so there is not not too much of a question. It's still there is, but if it were cylindrical, then there's a question of symmetry. Now what we assume over here, let's put this assumption very clearly, which is this is my rectangular slab, and I'm going to consider diffusion in this region, in this direction, which is x. Okay, and diffusion in the y direction is neglected. Why? Because is assumed to be too long. Fine. So diffusion is neglected. Now if I'm doing it, so because of symmetry, my condition at, so this is my x equals, say this x equals 0. So at I think that is my x equals 0, my right. Now what would be the other condition? X equals L what? There are several possibilities with this, so you have to just pick one. Let's talk about the simplest now. We will do the little more complicated one next class. Continuity is the simplest form. So there you can have a Robbins boundary condition, which is a flux type, flux with concentration, or you can have simple continuity. So let's assume the simple one, which is continuity at this point. I think this is the B KAV C naught. Okay. So what is KAV? So this is so this is my at x equals plus minus 1. X is dimensionless, by the way, here. So how am I dimensionless? Just by dividing it by L. So C equals KAV times C naught, and the other boundary condition is the center x equals 0, del C del x equals 0. Right. So can we go ahead and solve this? Why don't you do that? So what would be my Laplacian? Simply d effective times del 2C del x square equals KVC. So again, you know, we are going to assume these two different limits of it. One is the 0th order and one is the first order, like we had been doing all through. So the 0th order is very easy. Why? Because it's simply KV, and you can just go ahead and straight integrate it. And then what's the solution? You know, you've done this umpteen times. For the first order, what's the solution? What is the solution of this? What? First order, this, what is the solution of this problem? No. Look carefully. First is you have to see what is physically meaningful. A sin x and B yeah, A sin x, B cos x. What is the problem with that? You know, one of them will drop out, and you will have a sinusoidal wave of concentration inside the matrix. Is that physically meaningful? No. So whenever you write a solution, the first thing you have to figure out whether it's physically meaningful or not, and that is not physically meaningful. So the physically meaningful solution would be exponential, and because you've forgotten how to do these things, which is a strange thing, that you know. So essentially, when you have a positive on this side, you will have a exponential, right? If you have a negative out there, then only you can have that. So, and that's not possible because, you know, that's not possible out here. So anyway, so the solution would be, so C equals A cos hyperbolic. I think what are we going to? I'm going to do this a little differently later. That is, do the dimensionless and all that stuff. But just to give you a sense, I think KV over D effective, I think. Why cosine hyperbolic x and sine hyperbolic x is just from the e power plus x and minus x, I get this. So what we're going to do now is use a dimensionless form of this. We can go ahead and solve this, but the advantage with making the system dimensionless is that you can just scale all the variables as you want, and you'll see that it's very easy to work with the dimensionless system. So, so what we do is make the system non-dimensional, and what will happen is when we make the system non-dimensional, we'll come up with numbers, dimensionless numbers, which are ratios of important time scales in the system, and that is one of the added advantage of making this system dimensionless. It comes out naturally, and these are very important numbers. So the first number we'll get is, in this case, is the Thiele modulus, and I have already discussed the Thiele modulus in the last class, if I remember, which is the ratio of diffusion time over reaction time. And why is this important here? Because these are the two dominant phenomena in the system, diffusion and reaction. So it's very important to have a sense of the ratios of these numbers. Why is it important to have a sense? Because if Thiele modulus is given as the ratio of diffusion time to reaction time, and if Thiele modulus is very large, that means that diffusion is limiting. Yeah. So that is something that, you know, you need to figure out here. So why don't you do it on your own a little bit? So I'll help you out with this. So say x hat, because we need to do this unless and otherwise there could be mistakes also. So okay, so this is all we need over here. So d effective times del 2c del x square equals kv into c. Okay, so this is how we define x. So you get d effective L square del 2 theta del x hat square equals kv into theta. So kv So, it should be in denominator, yeah. So, kV L square over d effective times theta. Okay. Now, this could be written as L square over d effective divided by 1 over kV times theta. Okay. So, this is phi square over theta. So, this, what is this term? L square over d effective is the TD, right? Transverse diffusion time. This is the transverse reaction time. So, you get theta phi square. So, this is your basic equation, del 2 theta del x square equals phi square times theta, and that's, and phi square is kVL square over d effective, and that's the ratio of the transverse diffusion time over reaction time. Fine. So, this is my dimensionless model, and my dimensionless boundary conditions are very straightforward. So, at x equals plus minus 1, you get theta equals 1 and x equals 0, del theta del x equals 0. So, this is very straightforward, and solution is also something I discussed. So, this is the solution, but you should write it as sorry, yeah. So, but I like, I think it's always best to write it as a cosine hyperbolic and a sine hyperbolic, because it's much easier. So, if you write theta as, say, a1 cosine hyperbolic phi x, okay, because if you look at your reaction equation over here, there is del 2 theta. Let me, so your equation over here is del 2 theta del x square equals p square times theta, right? So, the solution is theta equals a1 cosine hyperbolic phi x plus a2 sine hyperbolic phi x, right? So, del theta del x equals phi times a1 sine hyperbolic phi x plus a2 cosine hyperbolic phi x, right? Okay. So, next step is that at x equals 0, del theta del x equals 0. So, del theta del x at x equals 0 turns out to be phi times a2 cosine hyperbolic phi x equals phi times x equals 0, phi times a2, which is 0, which implies that a2 equals 0, right. So, what you get is theta equals a1 cosine hyperbolic phi x. Now, your other boundary condition is that x equals plus minus 1, theta equals 1. So, 1 equals a1 cosine phi x. So, with my a1 becomes 1 over cosine hyperbolic phi. Okay. So, my solution is theta equals cosine hyperbolic phi x divided by cosine hyperbolic phi. Okay. So, this is what I have over here, which equals C over kV C naught. Okay. Now, what we intend to do now? What we intend to do is find my effectiveness factor. Okay, eta. So, eta, if you remember, was defined as R of V average. Okay, over R of V average, R of V evaluated as CS. Okay. So, my CS is x at x equals 1, right? CS is defined at x equals 1, which is given as kV C naught. So, the denominator is known. All you have to do is evaluate the numerator, kV C naught. Clear? So, how do you evaluate the numerator? Well, yeah, I think you can use that, but I think one of the other ways, yeah, that's also you can do. You can, because we got the theta, you can just evaluate the surface and do that. And another option is what I have on the screen over here. Just use this straight away. Okay, calculation of eta, this one. So because you know what is the volume of your slab. So and what you got over here is this is a slight typo. It should be this one should be RAV average. There should be a bar on the top of it. So minus RAV average is simply going to be 1 over V times RV times dV, and that equals what we got. So K C times dV, right, equals K times kV times C naught into theta times dV, and dV you can cancel out area on both sides, so you will get 1 over, I think, 2L. This goes from minus L to plus L, K kV C naught times theta into dx, right? Is it right? Okay. So then you can write this, take this 2 out and write this as 1 over L going from 0 to L, K kV C naught theta into dx. Fine. So what would be the integral? If I have a cos hyperbolic, it will simply be a sine hyperbolic, it will be the integral of that. So I think, yeah, that's, so no, that's not right. So minus RAV equals 1 over L 0 to L K kV C naught. Theta was what? Cos hyperbolic Px divided by cos hyperbolic Phi, I think, over dx. Now this goes as K kV C naught okay. Now this integral turns out to be, this whole thing turns out to be K kV C naught over L into, this is slightly complicated integral. So this comes out to be this tan phi, this cos hyperbolic phi x 0 to L divided by cos hyperbolic phi comes out to be tan phi over phi. Okay. So you can do that. What you have to do is essentially, because this will be sine, so you have a cos, but this 1 over phi will come, okay, because of the integral. Fine. Is it clear? So this will be sine hyperbolic phi over cos hyperbolic phi is in the denominator, you get a tan hyperbolic phi. So my eta is going to be, what is my eta going to be? So my eta, so let's go back here. Eta is this, RV this, and there's a K actually here. Okay. And I think the L should go from here because, yeah, because there'll be, L and, this, if you put this in the dimensionless coordinates, because X is in the dimensional coordinates, what do we used a hat over here, right? Yeah. So if I convert, so this is a hat, and if I convert this with a hat, then you got a L over here, then the L would go. Is it clear? Yeah. So this is what you have, and then your eta is going to be, RV over RVCS now. Which comes out to be K kV C naught over K kV C naught tan hyperbolic Phi over Phi equals okay. So this is what we get, and this is a very important formula to remember for eta, because I'll show you later, maybe in a couple of lectures or so, that this is something that you can use independent of geometry, because though as you change the geometry, and we'll do in the little time we have another geometry, you will see it's different, but what happens is that overall, be it a cylinder or a sphere or a slab, the effectiveness factor is more or less close to tan hyperbolic phi over phi, more or less close to. So if you use this number, you are not really very off. So this is something you might want to remember, this formula. Okay. So this is just going through what was done over here. The same thing you'll get, tan hyperbolic phi over phi. So just exactly the same thing. So what we do now is that in the next 10-15 minutes we have, let's quickly do this same thing, and I want you to go take the lead on this. Is take exactly the same thing, but this is there's a typo over here. This is not a rectangular slab. So I want you to do this in a sphere. So this is that example we had before, much before, the picture I showed you, where the enzymes are actually trapped here. Here. So the enzymes are actually strapped within, and this is a very common example because when you take some of your capsules, for example, enzymatic capsules, they are these spherical bead-like stuffs, and the enzymes are entrapped. So this is a very physical, very practical example. So this is the one that I want you to look at now, and because I showed you how to do it, so what I want you to do in the next few minutes is go and do it for the sphere. So first write your, so this is again your basic equation, right? This is again your basic equation. All you have to do is write your Laplacian in the spherical coordinate, and then go and make it dimensionless, and then go and solve it. So just start doing it, and I'll help you through the way. So if you have written the Laplacian, I don't know, some of you might have forgotten, but if you haven't forgotten, then this is what you have on the screen is the Laplacian in the spherical coordinate, right? So d effective again over r square ddr of r square del c del r. Now what are your boundary conditions going to be? Yeah, because we have assumed symmetry. So the basic assumption out here is that it's symmetric, and once it's symmetric, if it's non-symmetric, for example, let me ask you this: for a spherical substance, if it's non-symmetric, so what would be the? Can you write a 2D model for a non-symmetric sphere? For a cylinder, for example, if it's symmetric, okay. So this is my the effective Laplacian Kc, let's say Kc. So for a cylinder, what is my Laplacian? 2D Laplacian is 1 over r ddr of del c del r, right? Plus del 2c del z square, right? This is for a cylinder. Now this is for a symmetric cylinder, right? Symmetric cylinder. Now if I ask you for a symmetric sphere, can you write the 2D model? What would that be? Two-D model for a symmetric sphere. So let me add the, let me close my eyes and add the radial part, okay? Plus what would the other components be that would come in? Maybe theta and phi, but I asked you to write a 2D model, so which one would you choose? Why is that?
I'm taking R as a symmetric part. Phi theta is a symmetric part. Within a disk that every field we have a same conservation.
Yeah, but think about it physically. The sphere is the sphere has there's no in a cylinder you have this axis of symmetry, okay, and you're taking symmetric about the radial coordinate, right? but how would you physically denote that about this axis of symmetry you have symmetry? Is it possible to do it in a sphere? It's not. Think about that. In a cylinder you can do it, because in cylinder you can fix your axis of symmetry, and you can say about this you can. But in a sphere, theoretically it's possible, but physically is it possible to denote the system and say that there is there's an axis of symmetry? It's not possible, right? Then what would be your answer? The answer is that it is not possible to write a symmetric 2D model in sphere for a physical system. Theoretically mathematicians can write, but as engineers, there's no point, do you understand what I'm trying to say? That at what point, how are you going to denote your axis of symmetry and say that only around this there is a symmetry? Okay, because if there's a symmetry in this direction, then if there is no physical demarcation of that, and if you turn that sphere around, then there is no symmetry. So if you have to write an isometric model, the right way to do it is actually go and write a 3D model. You can both in phi and theta. Is it clear? Okay. So let's go ahead with this. I don't think we'll have the time to finish this. So the boundary condition is that symmetric boundary conditions, because we've assumed symmetry, r equals 0, del C del R equals 0. Fine. What will be the other boundary condition? Straightforward, that on the surface the concentration is given by kV C0. Fine. So how do you solve this now? So the surface is given by r equals Rm. So how do you solve this now? So one of the things that we can do is we can safely close our eyes and make the system dimensionless. Okay, for the sake of simplicity, my dimensionless variable would be Rm. So say zeta is given by R over Rm. Then my governing equation is given by this 1 over psi square dd psi of psi square del C del psi equals phi square times C. Fine. So no, solution is not Bessel function. You need to go and brush up your mathematics. So let me go back a little bit. We have completely run out of time, but because you have mentioned Bessel function, so what is the which coordinate is the Bessel function actually in the cylindrical coordinates, right? So I didn't do the cylinder, but that doesn't mean that you have to go back and do the cylinder now. So this is my d effective ddr of r del C del R equals kV C. Right. So after making it dimensionless, you get 1 over r ddr. This is the cylindrical coordinate, by the way. Don't confuse with spherical. So we have left the spherical where we were. So because he mentioned Bessel function, that's why I'm going back to p square of c. Fine. So what would be the solution of that? The solution of this is going to be Bessel function. So this you can write as del 2c del r square plus 1 over r del C del R equals p square times c. Multiply this by r square both sides, then you will have r square del 2c del R square plus r del C del R minus c square r square c, right, equals 0. So then your new variable, you have to what is the next step? You define a new variable. Y equals phi times r. Okay. So then your equation becomes okay. So now you can use a Bessel function solution. So this is your function solution. What I want you to do, I'll stop here today, but what I want you to do is to complete this Bessel function solution, because these are things that you need to review on your own, and I cannot review this in it's not a maths class. Complete this Bessel function solution and come up with some clue on what would be the solution of a spherical thing. So the flat plate was very easy. It's a cosine hyperbolic and sine hyperbolic. This is the Bessel function solution. I gave you the solution, but all you have to do is figure out what kind of Bessel function of first kind, second kind, modified, what kind of Bessel function is going to be. So you figured that out. And the last thing that you have to do is what would be your solution in the spherical coordinate, which is the most pretty interesting. thing to do. So I'll leave you at that. If there is any question on the part that we did today, so what we essentially did was, let me talk conceptually for 1 minute about what we did. And the whole thing, the whole lecture kind of pins on this idea of the pseudo homogeneous model, and the basic idea that we try to discuss is that for a pseudo homogeneous model is really actually for a heterogeneous system where there are these different point sources or sinks of reaction, and essentially if the two conditions on which you can do an averaging, one is that the microscopic length scale of the microscopic scale over the length scale of the macroscopic scale is much smaller than 1, and second is that there is no large variation in concentration over the entire domain. It shouldn't be that concentration is very small at one place and very large in another. If these two conditions are satisfied, then you can average it over the volume and come up with a homogeneous model, the pseudo-homogeneous model, The main characteristic of the pseudo-homogeneous model is that diffusion and reaction occur parallelly in the pseudo-homogeneous model, while it doesn't occur parallelly in the heterogeneous model. And then you can just write the diffusion equation and solve it. So these are two things I want you to come up with. One is the final Bessel function solution, and second is how to solve it in the spherical coordinates. So tomorrow we'll start off with that. What's that?
Error function.
No, not error function. No. So just a trick, you have to do this, and so we'll stop here. Thanks.